Welcome back to my course Aspects of Biochemical Engineering. Now I was discussing the transport phenomena, which appears to be the most interesting and most important topic as per any chemical and biochemical processes are concerned. Now, if you look at our biochemical process, we required the movement of the fluid, and when a liquid is flowing that through a pipeline or in a blood vessel, there is a kind of momentum transfer that will take place, and in a vessel, when you have some kind of microorganism that also or any when you do any kind of stirring, then this should be remain in suspension. So, we come across different type of transfer phenomena. One is called momentum transfer, another is the mass transfer, and the heat transfer. So in the last lecture, I try to concentrate on the momentum transfer and how you can analyze the momentum transfer. I try to discuss how the Reynolds number plays important role in case of momentum transfer. And today I want to discuss the mixing. That is another very important aspect of the chemical and biochemical industries, that how this transfer phenomena plays very important role. First, let us know that what do you mean by mixing? Mixing means that what we mean that which makes the uniformity in the reaction mixture. As for example, the physical operation which reduces non-uniformity in fluid by eliminating the gradient, concentration, temperature, and other properties. Now, what I try to mention, suppose this is a vessel, am I right? And suppose here you put your media and then you put your cell. Now, I told you cells are very much specific, as they are very much specific as per environmental condition is concerned. Under a particular environmental condition, they give the desired product. Am I right? So, if it is so, the temperature control is very important. Also, the nutrient concentration plays in the media, that also plays very important and role. So, that is the mixing determined how uniform is the temperature, how uniform is the concentration in the reaction mixture. So, which is very important. And mixing accomplished by the interchange of material between the different location to produce the mingling of the components. So, mixing plays very important role in the chemical and biochemical industries. Now, mixing involves several things. One is blending of soluble components of the media, such as sugar. Suppose we make a solution of sugar in the day-to-day life. In our home, suppose we want to make a solution of sugar, we put a spoon, with the help of spoon we make a solution. So, this also kind of mixing that we have. Now, dispersion of gases such as air through the liquid in the form of small bubbles. Now, I told you in case of aerobic fermentation process, that your main limitation is the dissolved oxygen concentration in the fermentation broth, because microorganism will take the oxygen that is dissolved in the fermentation liquid. So, dispersing of gas through the air in liquid in the form of small bubbles. This is also a mixing, that also kind of mixing that we have. Maintaining the suspension of the solid particles such as cell. I told you, just I explained that cells, when if you uniformly suspended in the media, then and only then it will freely interact with the substrate molecule and give the product. And where necessary, dispersion is in immiscible liquid to form an emulsion or suspension of fine droplets. So, in that case, what we do, we make a very fine droplets. As per, I can give the example that lipids, as per example, they are basically insoluble in the water. Am I right? So, if we want to solubilize the lipid, it's very difficult to do that. So, what we can do, we can disintegrate this fat globules in the finer globules, and it can make in suspension, which is usually done in the dairy industry, and promoting the heat transfer to and from of the liquid. That heat transfer also plays very important role. Now, question comes, what is the mixing components we have? What are the things we required for mixing? The basic thing we required a sapt. What do you mean by sapt? What do you mean by sapt? This is where the impeller is mounted. This is a sapt, this is sapt, and this sapt, I told you that this sapt should be perfectly straight. A few company in the world, they produce only that sapt for the bioreactor, because in the bioreactor the sapt plays very important role. Why? Because suppose this is a bioreactor and this is a vessel, this is a vertical sapt, and this is the impeller. Now, here I told you this is, we have mechanical seal. Now, this mechanical seal, this is required both for the chemical and biochemical industry, am I right? Now, in the biochemical industry, the mechanical seal plays very important role. The reason is that there should not be any entrance of the air from the, because since it is a moving sapt, so there is every possibility air can enter into the vessel, and air comprises a lot of different microorganisms, and then if it entered, then whole fermentation process will be spoiled. So, this is a special type of regulation is done. Now, that is why that, and another one important thing is that this should be perfectly straight. Now, if your sapt is not perfectly straight, then what will happen? If it is a little bit angle like this, then what will happen? Then there will be that, that suppose this is sapt and here we have the packing material. Now, this is all packing material that we have, and this is the sapt we have. Now, we are so here if there is the angle, there will be a friction that occurs in the mechanical seal, and that causes the spoiling of the mechanical seal. So, it is very essential. Another thing is that impeller, we have different type of impeller, different type of mixing, we require different type of impellers. Another requirement we require, this is the baffle. Why use baffle? We require just to stop the vortex. This, if you don't have this impeller, then we will be having this kind of vortex formation in the system. Now, different type of impellers we have anchored, we have propeller. This is largely used in the chemical industry. This is 6-blade flat blade disc turbine. This is used in the fermentation industry. So, that paddle impeller, gate anchor, and the helical screw. There are different type of impeller we can use. Now, now viscosity plays very important role as per use of different impeller is concerned. Now, in anchor, that usually lies in between 10 to the power 2 to 10 to the power 3 centipoise. Then the propeller is propeller which is mostly used in the chemical industry, that is 1 to 10 to the power 4 centipoise. Now, in flat blade turbine, which is mostly used in the biochemical industry, it is 1 to 10 to the power 4 paddles and other type of impellers that is also used. There are different type of the flow patterns we have. One flow pattern we call it radial flow impellers. So, radial flow impellers, what do you mean by that? Now, this is actually if you look at this particular schematic diagram, you can find out what you mean by radial flow impeller. So, when the agitator moves like this, then what will happen? This liquid is throwing like this, am I right? This is coming like this, and then it rotating like this, and here also it is there like this and coming like this. So, this is like this. This kind of flow pattern is there. Now, if you take the top view of this radial flow impeller, we will get this kind of. This is the disc, and on the disc and if you look at the side view, it will look like this. In the disc, the blades are mounted, and this is here we have the shaft. So these are the blade. This is called blade, and this is disc. So one experience I want to share with you, that I worked with Citogia Biochemicals, and we observed that number of blades that that we must have at different height, because I can tell you that like this. Suppose when you use the very large fermenter, so you have very high height. So naturally, if you put one impeller at the bottom, it may concentrate mostly on particular zone. It will not be effective throughout the media. So you have to have different impeller at different heights. They will be parallelly mounted like this, so that you can have proper mixing. Now question comes that what should be the configuration of this blade, that in the disc, that whether it is 444 or 555 or 666 or 776, or there will be 456 like this. Now we have find that in the industry, this number of blades, since that blades causes lot of friction, and number of blades very important role for the vibration of the reactor, and that we shall have to find out experimentally what combination will be most suitable for this particular fermentation process. That we can find out, we determined experimentally. So let me tell more details about the radial flow impeller. Radial flow impeller have the blades which are parallel to the vertical axis of the shaft and the tanks. I just explain. Vertical means this is the vertical. This is at different vertical position your impeller are mounted. Now liquid is driven radially from the impeller against the wall of the tank. That I have just shown you how it rotates like this, how it rotates like this, that I have shown you. Radial flow impeller sets of circular flow which must be reduced by the baffle. That that kind of movement will be reduced by the baffle. And why the baffles is required? We want to maintain the uniformity, the height of the liquid. And if you don't use the baffle, then we have vortex formation. The example of the radial flow impeller is the Ruston type of impeller with the 6-blade Dix turbine. I showed you what is the Dix and what is the blade, flat blade that we have. Now another thing that we have, what we call axial flow impeller. Now let us see how it looks. Axial flow impeller. So you can easily find out there the pattern is little bit different as compared to radial flow impeller. Here you find there is an angle. Now in case of previous thing, it was perpendicular with this. Am I right? Now here it is not the shaft. This blades are not in the perpendicular. It is kind of angle they are maintaining like this. Angling they are maintaining like this. So some kind of angle is there. And if you look at the flow pattern, it's a little bit different as compared to radial. So here it is like this, it goes like this, and it goes like this, like this. Now if you look at the radial flow, it is something different. It bottom one concentrated the bottom part, and this one concentrated on the top or upper part. But here it is not like this. Here you see that here it is governed by the whole thing. So it's like this. This pattern is little bit different, and here also we have shown that. Now let us do little more analysis. The axial flow impeller have blades which make an angle less than 90 degree to the plane of rotation and promote the axial top to bottom motion. That I have shown you. It is top to bottom motion is there. Fluid leaving the impeller is driven downward until it is deflected from the floor of the vessel, and then spreads over the floor and flow up along the wall before being drawn back to the impeller. I have shown you this, and when this is useful when strong vertical current are required. The example is pitch blade turbine. The mechanism of mixing. What are the mechanism of mixing? Mechanism is mixing is the three. One is distribution, dispersion and the diffusion. Distribution we consider as the macro mixing, and dispersion it includes both micro and macro mixing depending on the scale of fluid motion, and diffusion we consider as the micro mixing. Let us see that what do you mean by that. Now distribution we distributed. That means what we mean, the process whereby materials are transported to all region of the vessel by bulk circulation pattern. We are circulating by maybe we are circulating the in a manner it is circulated at different part of the vessel, and it is often the slow step of the mixing process, and factors affecting the distribution are size of the circulation path taken to the transverse path and regularity of the liquid pumping at the impellers. So, this depends on these two factors. Now, the important is the dispersion. Dispersion is that the process of breaking the fluid flow into smaller and smaller eddies. I have shown you already eddies, how eddies are created, a region of rotational flow. The dispersion facility facilitates the rapid transfer of material through the vessel, throughout the vessel, and degree of homogeneity as a result of dispersion is limited by the size of the smallest eddy which may be formed in a particular fluid. Next is the diffusion. Ever in turbulence media, that the region very close to the phase boundary is mostly by the thin layer. I can tell you, suppose this is a liquid and there is a bubble here, then so here you have two boundaries, am I right? This is liquid and here is a gas layer. So diffusion that takes place across the mixing, those regions mostly take place with the molecular diffusion. I can give the example of how oxygen is diffused into fermentation media from the air for aerobic fermentation process, particularly in case of surface culture. Now, mixing time, how you determine? The mixing time is the time required to achieve given degree of homogeneity starting from the completely segregated state. That means, suppose this is a liquid and you put some material here. Now, question comes, mixing time is how quickly it is dispersed into the media. That means how that time required for the homogeneity of the reaction mixture. Now, it can be measured by injecting a tracer, and tracer might be anything. It might be acid solution, maybe alkali solution, maybe color, anything we can have, and or maybe any salt solution, and following its concentration with the fixed point of tank. And your monitoring device might be several. In case of acid or alkali, you should have pH. In case of sodium chloride, you use the conductivity detector. In case of color, we can have some colorimetric estimation process that we have. The tracer is commonly used acid, base and concentrated of salt solution. Corresponding detector is pH probe and conductivity cell. Now, how the mixing takes place? Let us give the example. Suppose this is the vessel, and this is the starter that we have. This is liquid. Now, when suppose I am putting 1 milliliter of one normal HCl solution, let us take the example. Now, when we add this acid here, then what will immediately it will not be uniformly mixed. So, what will happen if we consider here concentration of the acid or pH, suppose you consider here pH, you will find pH will your acid, that concentration will keep on at a different, it will keep on increasing, decreasing in the media, and finally you will find the homogeneity in the reaction mixture. So, you have so many wave type of characteristics that you will find, and after several wave you will find that uniformity in the reaction mixture, that final concentration minus initial concentration that you can find out. So, what I want to mean that here this curve, this is the wave that we have, this time between these two peaks we consider as, because if you consider these two peaks we consider Tc, and what is Tc is the circulation time, and actually that we have observed Tm mixing time equal to 4 into Tc. This is usually the case that we have 4 such, we can, you see here how many things, 1, 2, 3, and we consider another thing is more or less is constant, 5 also sometimes may be applicable. So, circulation time, how you define is the time period between the two subsequent peak of the response curve, and there is a approximate relationship that Tm equal to 4 Tc. Industrial scale vessel working volume in between 1 to 100 cubic meter, mixing time varies in between 30 to 120 seconds depending on the conditions. So, this is 1 to 100 cubic meter reactor. If you have this mixing time is coming about 30 to 120 seconds. Now, let us try to solve the mixing time that in case of, we have seen in case of Rootstone turbine can be estimated by the following equation, and this is applicable when Reynolds number is more than 5 into 10 to the power 3. Then this is the rotational speed of the agitator, this is the mixing time equal to 1.54 volume of the reactor, and di is the diameter of the impeller, and Reynolds number is equal to d. This is called, this is not the normal Reynolds number, this is called agitator Reynolds number. Okay, this is called agitator Reynolds number. So, there is a problem, that how, let us see how we can solve this problem. A fermentation broth with viscosity 10 to the power minus 2 Pascal second and density 1000 kg per cubic meter is agitated in a 2.7 cubic meter of baffle tank using Rootstone turbine with diameter 0.5 meter, and starter speed is 1 the second inverse. Estimate the mixing time. How we can solve that? Now, I told you that when you try to solve any problem, please note down the whatever the data is supplied. So, we have the density is given, viscosity is given, and viscosity, whenever you have this kind of data, try to convert into the same unit. This is the SI unit, so you convert into the SI unit. Then this is diameter of the impeller we consider as 0.5 meter, and Ni is 1 second inverse and V is 2.7 cubic meter. Now, first we shall have to find out the Reynolds number. We can find out this equation. This is 0.5 is the diameter of the impeller, then it is coming about 2.5 into 10 to the power 4. Now, this indicate this is more than 5 into 10 to the power 3. So, this equation is implies. So, since this equation implies, we put all the value here to just to calculate the mixing time, and mixing time is coming about 33 seconds. So, we can easily solve the problem. Next thing I want to share with you that we carried out some kind of experiment in our lab, and just to find out that how to calculate the mixing time and how it correlated with power drawn by the agitator and the Reynolds number. Now, we use the bioengineering AG fermenter and the pH probe. I told you whenever you do that, you have to use some kind of monitoring device, and pH probe is required. Then other things require syringe, stopwatch and other control unit. Now, here we use the CMC solutions is the carboxymethyl cellulose. And why carboxymethyl cellulose? Because carboxymethyl cellulose, though it is insoluble in water at normal temperature, but if we heat it with constant stirring, it will become soluble. But when you cool it down, then characteristics of the CMC solution will be same as the characteristics of the fermentation broth. And another important factor is that when you add acid or alkali, then what is happening? That there will not be change in the chemical structure of the CMC. So, this is how the CMC is defined. This is the polymer of cellulose C6H10O5N, and this is the methyl group, and this is the carboxylic acid group. Now, working volume is 2 liter, and we take 10 gram of CMC solution, and we also prepared 1 normal HCl and 1 normal this NOH solution. Now, this is the methodology how you can prepare CMC solution. I am not going in details. Now, for finding out mixing time, we put the CMC solution and we maintain the temperature at 35.3 degrees centigrade with the initial pH of 6.36. Then what we have done, that agitator speed, first we control the agitator speed at different level. First we consider 100, then 1 milliliter of 1 normal NaOH solution is added to the reactor and stopwatch is started. As soon as we add, we put on our stopwatch and find out how long it takes to maintain, to have the uniform pH. So, this to obtain the stable pH, the stopwatch is stopped and time is noted. Similarly, we can add 1 milliliter of 1 normal HCl solution, and we can also monitor the time required for having the constant pH, that we can easily find out. The same process is repeated in case of starter with 200 rpm, 500 rpm, and the corresponding mixing time is noted down. So, this we carried out in the lab. Then this is the table that we prepared. You see that on 100 rpm, you have test 1 and test 2. This is initially take 140 40 seconds to have the uniform pH, and when you use the base, it take 135 seconds. In second case, when you use one acid, 150 seconds, and second case is 140 seconds. So, we take an average of this and we find the mixing time this. Similarly, we can find out the value at 200, 300, 400, 500 and 600 rpm. Now, we prepared a table like this at different rpm. What is the power number, what is the that power consumption by the agitator and Reynolds number. The question comes how you did it. That Reynolds number, if you look at the Reynolds number, how you calculate, with this the agitator Reynolds number, rpm is that 100 rpm, we can write this is rps, 100 by 60 is the rps per second, and di is 0.005 millimeter, and then we can find out the Reynolds number is this. And then we find out we know the rho value is 1000 kg per cubic meter and viscosity is 0.5 kg per meter per second. So, RE value can be easily calculated. Similarly, we can calculate also the power drawn by the agitator. How you can do that? Power drawn by the agitator is the NP. NP is the power number in the rotational speed of the starter. Di is the diameter of the impeller, and rho is the density of the liquid. So, everything is known. We put the value, we can find out what is the power drawn by the agitator. So, we can easily calculate. Now, here I want to show you that different region we have lamellar flow, we have transition flow, we have turbulent flow. The turbulent flow, I told you, it is lie in between 10 to the power 4 onward, but in between approximately the 10 to the power 2 to 10 to the power 4 we have transition phase, and lamellar flow is usually the Reynolds number 1 to 10 to the power 2. So, this is the reason that we have now different type of impellers, they have different type of pattern. This is the different type of impeller is applied. Let us assume that if this is the that is the this is it may be applicable for if one might be applicable for propeller and the impeller may be another paddle type of thing. So, as per our requirement we shall have to find out, if you know the Reynolds number, we can correspondingly we can find out the power number. Then we can calculate in this equation. I have shown you the calculation, we can find out. So what we can find out in the table, we have the table, we have N value and we have RE value, that N is the rotational Reynolds number, and then this power drawn by the agitator. We can have different values here. So, what we can do, we can make we can draw a curve. This is power drawn by the agitator and this is the mixing time required. So, if you draw, you will find this. The why this curve is important? The reason is that we try to find out at what is the minimum power required to have the minimum the mixing time, the max this is the value that here you see, even after this if you increase the power of the agitator, it is not going to decrease the mixing time significantly. So, we shall have to, for design purpose, we shall have to consider this we can assume this kind of power is required for proper mixing of the particular vessels. Now, here there is another correlation of the Reynolds number and mixing time, that also we can draw. So, in this particular presentation I try to discuss the how the mixing that involves the transportation of the fluid, because this how the different material they flow in that mix in the system, because main purpose of mixing to maintain the homogeneity in the reaction mixture, particularly it is essential in any fermentation process, because we know our microorganisms are very sensitive with respect to the environmental parameters, with respect to substrate concentration. So, so this now we try to find out how the mixing time we can determine. The mixing time is the time required to make the homogeneity in the reaction mixture, and I told you this is equal to Tm equal to 4 Tc, and also we try to find out the mixing time in a particular fermentation process, and finally we discuss some kind of experimental trial that we have carried out in the lab, and how you correlate with the power drawn by the agitator, and which is very much essential for designing any fermentation process. Thank you.